with one form. Why we need differential forms? There are various reasons. But one of the fundamental reasons that we want to turn our things, especially notions in calculus, we want to turn them into the differential forms because they are reversed. So usually when we define dx or maybe differential of a function, okay, it has in classical calculus meaning of infinitesimal set. And you use some tricks to define it. But otherwise this doesn't have a very precise meaning. But if you interpret this guy linear algebraically, okay, or you treat this as a linear map, then you have a rich theory of linear algebra to talk about the same things in with much more foundation side. Okay, so that's precisely what we want to do. We want to turn our fundamental calculus, other things which you have learned in, for example, 3D geometry or vector calculus. We want to turn them into differential forms. You learned some bits of that also when we were doing vector calculus, but now we want to do it more kind of rigorously. Okay. So what are one forms? We know that for us, vector space is basically tangent vector space. So a map phi, okay, which is a linear map
TPRN
from TPRN
to R.
into R. So a linear map phi from TPRN to R is one form. So every linear form is a one form. Okay. If I want to write it precisely, what does it mean? In other words, that if at this point P I take a tangent vector, which is xp, okay, and maybe I have another tangent vector, yp and some scalars, then this phi is doing what? It's preserving the scalar multiplication and addition in the tangent space actually. So it preserves it. So when we, oh, yp, yeah, it should do what? It should do yp obviously. Okay. So once we have this, and okay, like we so in usual sense we call them O-vectors and so on and so forth. We will discuss all this in detail. So what next would you like to do? I would like to define this notion of differential. Okay. So if f, which is a map which takes a point from Rn and gives you a number r, okay, which we usually term as a scalar field, okay, is C infinity, okay, it's like a smooth function. Then I can define differential to be a one form actually. In other words, it's a map, okay, from TP equal
But tangent bundle.
okay, so like I can define define it in a much more generalized manner. So instead of taking, TPRN, I can take a tangent bundle, okay, of Rn and assigns it a number. What is the way to assign it a number? That if you take a vector field, okay, and if I apply a differential on it, okay, then the outcome is, so I want to have a number. So how can I have a number using a vector field and a scalar field?
Gradient
Yes.
dot
I
product
can do what? I can compute the directional derivative
of f.
Okay, of f in the direction of this whole vector field. Okay, I know it's like a number. It would be, more precisely a number if you do it at a particular point. Okay, so I can do it at an arbitrary, essentially, point. So in other words, if I am, okay, so this means df operated onto x section. So let's treat this as a map. So Rn into R, in other words that if I have this map operated onto point P, then it gives me what? It gives me the directional derivative of f in the direction of the vector, that's P actually. Okay? And which I can specifically write, in classical calculus terms. And this would be the gradient of f
dot product
and its dot product.
vector part
Vector part of the x.
Evaluated at P.
Everything should be evaluated at P. Is it making sense? As you can, so let's, if I treat df as a linear map, not a one form, okay, then we know that every linear map, okay, or even a tensor, no matter what rank you have, you can specify it by its action on, on the basis actually. So in other words, if you want to know what is, a linear transformation operated on a vector V, okay, it's enough to know that what is the linear transformation, okay, of, bases actually, E1 and what is E2 and E3, because then you can express this TV in the terms of these actually. Okay. Similarly, can I do something like similar here? The answer is yes. Okay. And what would be the kind of basis actually? Here it is going to be. So in other words, if I have TPRN, okay, what are the bases for this?
Partial
space.
Partial.
So it's partial by partial x1 up to partial by partial xn actually. Okay. And if I have, so it's like collection of all one forms. Okay.
ये कटता है ये
partial
by partial x.
Yes. So you have to yes. You have to also evaluate them at point P actually. So you have to always. So when you are writing P, that means that you have to evaluate them at what we call point P. So what would be corresponding essentially dual basis to this? So the dual basis to this is going to be
This case of differentials.
so the differentials of the coordinates actually. Okay. So take the coordinates and compute their differential under the but these differentials are what? Linear maps as the definition. So each one of them is a one form. dx1 and okay, so on and so forth, and dxn. I think we have to also evaluate them at p actually. not n, but n. We must write at the top actually. Okay? So this is kind of dual basis actually. You know, the basis of the vector space. And we also discussed previously that we call such a space as this collection of all one forms that you can have on the tangent space at the point P. You call it as a cotangent space actually. So that's a cotangent space. Okay. Is it really so is this basis a really dual basis, you know, to these? The answer is yes actually. So how you can have it? So if you apply dx psi, okay, and operate it on, you know, the basis of the basis tangent vector actually, okay, then what would be the outcome? The outcome would be, now, so it's like, so when the df is operating onto, you know, a tangent vector, in other words, a vector field is specified at a point, so it gives us what? It gives us
partial
gradient,
psi by partial
directional derivative basically. Okay. So when I compute this, what do you think? What I'm going to have?
component ij only.
I think we must take different components. Yes.
Chronicle data.
Okay.
Partial xi.
Then this is going to be, by definition, partial xi by
partial xj.
partial xj. In other words, you have to simply apply it. Okay, on each coordinates, and so you know, using the gradient definition, and this would be same as delta ij. And then we can see actually that what does this shows that indeed, you know, these one forms, okay, differential forms are dual basis to these tangent vectors actually. So one of the key things that we have to keep in our head. I would like to quickly remark, or maybe you can treat this as a proposition as well. Okay. In other words, with this machinery that we have, you know, kind of defined and developed. So in other words, okay. So you also learned a particular meaning of differential in your classical calculus. So it's like a vector calculus. Okay. So if this new definition of differential, if it is a true definition, then you must be able to recover your classical, you know, definition through this definition as well. Okay. So the proposition is that, okay, if you have a smooth vector field, if f is C infinity, okay, you know, it's a map from Rn to R, the scalar field, okay, and the x1 up to xn are coordinates. Okay. Coordinate functions. Okay. Coordinate functions in neighborhood U of P. Okay. Then I can write differential, okay, in the following manner. Which is going to be partial f by partial xi and dxi. So it's a sum actually, Einstein's sum. Okay. That's how you compute the differential when you compute in, you know, what do you call in the classical sense. Okay. So that's what I would like to show, that once you have this way of defining, you know, differential, then you also have, you know, this notion of differential as well. As I said that, you know, you can specify completely a linear transformation by operating it onto
Spaces.
the basis. Okay, so it's enough to actually. So in other words, if I, express this df on this side, or operate, one of the side onto the basis of what? So basis of, what do you call these tangent vectors actually, and see what happens actually. So that would be enough. So if I take df by dx psi, okay, partial f by partial xi and dx psi, and operate it onto xp. Okay, so tangent vector actually, an arbitrary tangent vector. What are you going to get? I know that I can express partial f by partial xi, dx psi. You have to keep in view that this is kind of a number actually, so when you evaluate at point P. Well, this is the vector, another scalar field, one form that is going to operate nothing. Operated onto xp. How can I write xp actually? So xp should have some component actually. So vi and partial by, maybe vj and partial by partial xj. I know that every tangent vector can be expressed in this manner, and then you have to evaluate everything at point P. Okay. Now, if this would be the case, what would be the output? The output would be like these are scalars. Okay, and so I can pull them out. So the rest would be vj partial by partial like psi and dx psi operated on partial by partial
xj.
J, everything evaluated at P. Okay, but we know that these guys are what? So vj partial by partial xi, and this is nothing delta ij. Okay, and everything operated on the P. Okay, and once I have this, what's going to happen? So you're going to get, so I can get rid of one, what do you call, index actually. So I can write this as vi partial by partial xi and operated on the P. Okay? And now what is this then? I mean, if you see, this is nothing. So like, so it's like, okay, v1 partial by partial x and v2 partial by partial x2 and so on. So it's the gradient of f.
Exactly at point 2.
Okay? And it's dot product with what?
X. Vectorial part.
Vectorial part of xp, which is
X.
the gradient of f at p times the vectorial part of px. Okay? And this is what? This is precisely this thing is. Okay? So what did you get? This is the same as
XP.
df,
XP.
okay, operated
On XP, operated on to XP.
let me say xp, yes, so we can.
XP pull out कर दें तो वो differential इसके बाद.
Is it making sense? So indeed, when you have this new way of describing differential as a one form or a linear transformation, like, okay, the classical things are preserved. In other words, every differential form can be written as, as this sinus times sum. Okay, so differential form is a linear map. Okay, so these dxi's are what? These are the bases actually. Okay, so it's like as you can write every vector in the terms of its basis, and it's like, so similarly for differential forms is basically essentially something similar. So you can write it in the terms of its basis, and these are what? These are the components of the basis, components of the given vector. Is it making sense? Some remark? If I have an arbitrary one form, okay, alpha, okay, then then alpha is a member of this cotangent space actually, right? Member of this cotangent space. And these are the bases of the cotangent space. So in other words, I can express this in the terms of the linear combinations of these differentials. Okay. So alpha can be written as, some component. Okay. The AI. Onto X and AI onto X and dxi, something like this. Okay. These guys, these AIs usually, this A1, A2, and AN. Okay. These are called what? These are the covariant components. These are the covariant components of alpha. Okay, the abstract differential form. And we also discussed basically when we were kind of reviving or maybe discussing this, the very fundamentals of vectors and covectors. We said that vector components are contravariant while the bases are covariant. Okay. And similarly, in case of the dual space, okay, the components are covariant while the bases are contravariant actually. Okay, if you remember. So you have like this meet with this intuition actually. The components of one form are covariant, but these are contravariant actually. So in other words, if whenever I have to write alpha, I'll write in this manner actually.
Sir,
Where these AIs of X are what these so each one of them
Scalar function?
these are scalar functions. So these are C infinity smooth field set. Okay, so these are smooth functions. Okay.
sir, this basis is contravariant, right?
Which one?
This dual space.
Yeah.
And the spaces basis is covariant or not?
Which one?
And the TPRM spaces.
Yes.
That's covariant. So we are putting the index of subscript form.
Okay.
Is it just notation mistake?
No, it's not a notational mistakes. So let that agree with the notation that they are using.
Now we saw it.
Yeah,
Basis was
yeah,
covariant.
should be that manner, but let's agree with the notation. Let's start, using at the moment. Okay, and this is what precisely when you read it says here that like this is also all the time confuses the students actually that where to put the indices. Anyway, in other words, okay. So that's remark number one. The remark number two is that is every alpha, in other words, is every alpha can be written as the differential of some field actually. The answer is no. Okay, so that some can be and some can't be actually. So in other words, so does there exist a smooth function, okay, smooth function such that so let's say for alpha, for each alpha, does there exist a smooth function such that alpha is df? The answer is no actually. It's not necessarily that every one form is a differential of some scalar field. But if it is, if alpha can be written as differential of a scalar field, then you call alpha is exact actually. Okay, so it's like an exact one form. Okay, something that you have already done and seen after.
Sir, I have another question.
Uh-huh.
For defining one form, we have enough C1 space. Why are we taking C infinity? C1 would work.
No, I mean, okay. It is.
The differential
It
geometry.
is that sometimes you need to plug in these vector field and these what you call like this machinery into something, okay, for which you need C infinity actually. Okay. So in other words, we don't want any hassle. So I can use it anywhere I want. I can be sophisticated, okay, let's just assume, like we did in vector calculus, when we were doing differential forms, there we defined it precisely. You say that R form is a, a CR map actually, a CR map actually, and so on and so on. You can use, but like, okay, since we are assuming from beginning here that if you have a scalar field, and you assume it's C infinity, that means you can do it anything with it. So it's just a matter of convenience. But yes,
One from the C1 zero.
being mathematician, we have to apply what is called the Arkham-Razor principle. That don't assume
More than you need.
that you don't need it. Okay.
Very clear.
The cardia.
What would be some examples? So if I want to concretely write some examples, so what would be, for example, some examples? Okay, so that if you are in R3, what would be some example of? Something like
X
x squared dx plus xy dy plus
Z.
plus minus dz, so, something like that. So that's one example of essentially one form. Okay. That's an example of one form. The next is that on a cotangent space, I also defined it. Okay. That I can also define, so that I can turn a cotangent space, okay, at point P, into a vector space actually. Okay. So in other words, I can define the algebra of